Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. This is the third installment in the Adventures with Python series, in which we learn Python by building a text adventure game. No prior programming experience is needed, but you should watch the series videos in order. I'll link the playlist here and in the description. Let's get started. In the last video, we enhanced our game to move the player to a new room based on the command they chose using a serial if statement and Boolean logic. I don't know if you tried to continue programming the game, perhaps getting another command from the user and moving them to another location, but if you did, you might have realized that structuring the game this way will become unwieldy very fast. What I have here is an example of this same logic, but assuming we don't know the room the player is currently in. I'll run it a few times and change the current room each time I run it to illustrate. So here I'll set the variable room to cloister, and I can go in any direction. Now I'll set it to church, and I can only move south from the church. I'll move south, and it tells me I'm in the cloister. Then I'll run it again and try to move north. You can see it tells me I've bumped into a wall and I'm still in the church. This code is uploaded to the same directory on my GitHub repository as the other code, and it's called shabbyabby v2unknownroom.py if you want to play with it. There's a link in the description. I haven't tested it thoroughly, so it's possible I made a mistake with one of the rooms. Let me know in the comments if you find an error. Even though it's a bad design, it should work. In this code, we must check both the room and the direction to know where the player is going next. The logic spans 62 lines, and that's just for my tiny 5-room dungeon with only one exit off 4 of the rooms. And of course, code being long doesn't make it inherently bad. What's bad about this solution is that it will grow, maybe not exponentially, but ridiculously, for each new room I add. Because for each new room, I have to add another nested if statement, and I also have to add components to the other if statements where the rooms connect. Imagine this code, but hundreds or thousands of lines long, and you need to add a room or fix a bug. There's got to be a better way. In fact, there are many better ways, and all of them involve encoding the dungeon into a data structure that stores both room information and information about how the rooms are connected. We're going to learn about one data structure today, a list. In other videos, we'll learn about 2 others, dictionaries and classes. All of these data structures are very powerful. The final solution that we write today, with a list, will do what this program does, plus a little more. But the logic will be only 6 lines long, and the data structure will be easy to read and modify. You can add as many rooms as you like to the data structure, and the 6-line logic will stay exactly the same. Let's learn about lists in the console. I'm going to define a list. I'm going to type directions equals open square bracket, n in quotes, comma, s in quotes, comma, e in quotes, comma, w in quotes, and then close square bracket, enter. That is a list definition. Remember first that an equal sign is an assignment operator, and when Python executes an assignment statement, it associates the value to the right of the equal sign with the variable name on the left. To the right of the equal sign is a list. A list is enclosed in square brackets, and the elements of the list are separated by commas. The elements can be basically anything, so integers, floats, strings, or even other lists, as we'll see in a moment. This list consists of 4 strings, and you'll find this familiar. You can index into a list just as you can index into a string. So a list, like a string, is an ordered, indexable collection of elements. If I write directions, the name of my list, open square bracket 0, close square bracket, how do you think idle will respond? I'll press enter. Hopefully you remembered from string indexing that the index of the first element in a collection is 0, and you guessed that the first element of the list was the string n. And if I ask idle to evaluate directions, I get the whole list. What is the index of the last element? If you guessed 3, you're correct. Directions 3 is W. As with strings, I can get the length of the list with len. So len directions evaluates to 4. As with strings, because lists begin indexing at 0, the index of the last element is the length of the list minus 1. Now, let's learn another operation on lists. You might wonder why I created a list of direction commands. This is yet another way we can check if the user has typed a valid command. I can use the in keyword to determine if a value is in a list. I'll write n in directions, enter, and idle responds with true. X in directions, and idle responds with false. So value in list is a Boolean expression. It evaluates to true or false. That means I can put it after an if in an if statement. We'll come back to the console in a moment and look at some more operations on lists, but let's incorporate into the current program. I'm going to rename this program shabbyabbyv3.py, change the docstring at the top, and then define the list of directions under the docstring. This definition is a little different from what we've seen before, so let's talk about how and why. First, you'll notice that the name of my list is all uppercase. In the past, all of my variable names have been lowercase, and if made up of multiple words, those words have been separated by underscores. That is the convention for naming variables in Python. But constants are basically variables with values that are never going to change. You'll notice with the variable command, we get the value from the user, so we don't know what it's going to be until runtime, and it could be different every time the program runs. And we even assign a new value into it right after we get its value from the user. That's all very typical for a variable. But what if we have a value that we know before the program runs, and it's never going to change while the program is running? We could use the literal. For example, we could refer to the literal list, open bracket, NSEW, etc., every time we want to check if a value is in the list of directions. Or we could give it a short, simple name that will make our code easier to write, easier to modify, and more readable. Then it would be a named constant, a value that's never going to change, but that we've assigned a name. And the convention for naming constants is all uppercase. Therefore, I've named this constant directions, all uppercase. While the program runs, I'll never change this, and it will be the same every time the program runs. I've added the full word directions to it as well, north, south, east, west, and you'll see why in a moment. Finally, in my annotation, I've written list, open square bracket, str, close square bracket. That is because this is a list of strings, and that is how we write that annotation. You could annotate this simply as list, the data type for lists, but list open square bracket str close square bracket is more specific and therefore more helpful to anybody reading the code. Now, I'm going to revise my series if statement a little bit. I'm going to check first if command is in directions. So if command in directions : and then I'm going to select the north, south, east, west code and indent that. And I'm going to leave the else at the same level of indentation. This is a nested if statement now. Let's talk about that a moment. You can put an if statement inside another if statement. That's what nested means. One statement is inside another and will end before the outer statement ends. And you can always tell which elifs and elses go with which ifs by the level of indentation. So the if, elif, elif, elif all goes together, and the if, else goes together. Let's talk about the logic. This code checks first if the command given was in the list of directions. If it was, we'll go in and find which direction through the series if and print the new location. We know that one of these conditions will be true because these are the only options, so technically we could change that last elif to an else. Let's not though, just in case we decide to add some directions such as up or down. Now the else is at the same level of indentation as the outer if. Suppose the command typed by the player is not in the list directions. Then the test command in directions will be false, and will go straight to the else, and the program will print, I don't understand that command. So we have two branches. one for a command in the list of directions, and one for a command that isn't in the list of directions. And on the command in the list of directions branch, we're then processing the specific command. I'm going to do one other thing to simplify this. I'm going to add back the code that extracts the first letter of the command, but I'm going to do it after we know that command is in the list of directions. So under the if, command equals command sub 0. And then I can rewrite all of my tests to simply test for the first letter, N, S, E, or W. We can do that because if we're in here, if we're on the command in directions branch, then the command was either a single letter or it was a full directional word. If the first letter is N, the command wasn't no or nothing or never, it was north. Let's look at a few more operations on lists that might come in handy later, and then I'll show you how we can build a list that will give us an easy way to add rooms to the dungeon and just a 6-line block of logic to move the player around. Back in the console, we have our variable directions consisting of 4 elements, the strings N, S, E, and W. We can add to the list with the append command. For this we use dot notation, as we did with upper and lower on strings. You'll learn a lot more about dot notation later in this series when we learn about objects and classes. For now, just remember which commands use the dot notation, which is a variable dot and then parentheses, maybe with 1 or more arguments inside the parentheses, and which commands are functions like print and input, where you write the command name and then the parentheses, maybe with arguments inside the parentheses. So directions dot append and then parentheses. And inside the parentheses, I put whatever I want to add to this list. So why don't I add the string north? And enter. And now let's type directions. And you can see now it's NSEW north. So append will add something to the end of the list, whatever we put in parentheses. And let's look at remove, another command with the dot notation. Directions dot remove. And in parentheses, I'll put the string W. And if I look at directions, it's gone now. And north, notice, kind of moved into W's slot. There's no empty space where W was. It's like it was never there. You'll get an error if you try to remove something that isn't there. I'll try to remove the whole word south. If you want to avoid that, use in to check if it's there before you try to remove it. Let's look at one more thing that we're going to use in our final edit for this video, and that's index. If we want to know the index of an element in a list, we can use the dot notation. So I'll type directions.index north in parentheses, and I'm told 3. Again, that's where W used to be. Okay, now let's build a data structure that will hold data about the locations and how they fit together. I've got a drawing of the data structure here. The data structure is a list of lists. Each sublist contains the data for a location. The first 3 elements of the sublist are strings, the name of the location, a description, and then the text for the exits, such as, there is an exit to the south. The final 4 elements of the list are integers indicating what room you will move to if you move in that direction. The integers are actually the indices into this data structure for the room you're moving to. I've included the indices of the lists to the left because it's such an important element of this data structure. I'll show you this same list but with the values for our dungeon filled in. Now you might pause the video and take a moment to look at this structure and see if it makes sense, remembering that the last 4 integers are the indices into this very data structure of the place you'll go if you move in that direction. And the directions are always north, south, east, west, in that order. So now I'll explain to confirm your understanding or help you with it if you're not 100% on board. The location at index 0 in this list is the cloister. Remember that the only exits from the other locations are back to the cloister. So you can see zeros in each of the other locations. For the church, it's in the south location. For the kitchen, if you go north, you get to the cloister. For the library, west gets you back to the cloister. And for the garden, east is the exit to the cloister. You can use this like a table. Start with where you are. You're at the kitchen, go to that row in the table. You want to head north, go to that column in the table. From the kitchen, heading north, you go to index or row 0 in the table, the cloister. I'm using -1 as an indicator that there is no exit in that direction. In many programming languages, -1 is an invalid index into a collection. In Python, it's actually valid. A negative index in Python will index from the end of a list backward. But I'm going to check for -1. I'm not going to blindly take the index and go with it. I could have put anything there, including the special value none, except a valid index into this list. I chose -1. Now, look up at the cloister. Where do we end up if we go north from the cloister? There's a 1 there. So we go to index 1, the church, and so on. Now, I hope the data structure makes sense. Let's go back to our program and see how to build it and work with it in Python. I'm going to call the variable Abby, and I'm going to make this a variable, not a constant, because I think the dungeon could potentially change as the program executes. For example, imagine that the player finds a key that opens a new door. That information would then change in the data structure dynamically as the program is running. So I'll write Abby equals, and then open and close square brackets. Inside the brackets, we'll have a list for each location. There are 5 locations, so I'm going to put in 5 empty lists separated by commas. Abby is a list of lists. Let's create the list for the first location, the cloister. The order is the 3 strings first: name, description, and exits. I'll put in the strings cloister, you are in a courtyard, and there are exits to the north, south, east, and west. And the next 4 values are the indices of the locations in this list that you'll move to if you move north, south, east, and west in order. I'll put the church at index 1, the kitchen at index 2, the library at index 3, and the garden at index 4. And so I'll put 1, 2, 3, 4 as the rest of the list. That's the cloister defined. Let's do one more together, the church. So for the church, which is at index 1, so the next list, I'll write church. In front of you is a large stone church, and then there is an exit to the south. Now, for the directions, we can only go south, and that gets us to the cloister at index 0. So -1, 0, -1, -1. I'm going to fill in the other 3 locations now according to the data structure image. So that's the data structure defined, and hopefully you can see how to add rooms. Just add another list. So, for example, if I wanted to add a storage room to the north of the library, I'd add another list for that room. That list would be at index 5, and so in the library's directions, in the first slot, north, I'd put 5, and I'd rewrite the exit string. By the way, having directions and a direction string is a little redundant, and there is a way around it, but I didn't want to complicate this program right now. In the storage room's second slot, south, I've put 3, sending us back to the library. To annotate this structure, I can simply put list. Or I can be a little more descriptive and put list, and then list, and inside that list, string, str, bar, int. That means a list of lists of strings or integers. Now, how do we use this? I'm going to start by adding a variable, current location, and setting that to the index of the current location. I'll set it to 0 to start, the index of the cloister. Now, let's look at how we index into our Abby data structure to make our 2 print statements, you're in the cloister, and there are exits to the north, south, east, and west, more general. The name of the location in our data structure is at index 0 of each sublist. Let's create a constant for that. Up in the constants, name int equals 0. Then, instead of you're in the cloister, I'll write you're in the space, and then plus to concatenate, and then Abby sub current location sub name plus period. Okay, Let's pull that apart. Abby sub current location will get us to one of the sublists, the one for the current location. Right now that's cloister, so that will be the first sublist. That is itself a list, so we can then index into that. We're indexing into that with name, which is a constant with a value of 0. That will evaluate to cloister. If current location were 1, the sublist for the church, then Abby sub 1 sub 0 would be church, etc. Let's test that. And it prints I'm in the cloister. Let me change the current location to 4. Now it prints that I'm in the garden. Given what you know, can you modify the statement telling the player the exits to be more general? Pause the video and give it a try. The exits text is the complete sentence, so I can just write print Abby sub current location sub exits, and I'll make a constant exits int equals 2. That's the index of the exits in our sublists. Let's make constants for description 1, north 3, south 4, east 5, and west 6. So that's pretty cool, right? Whatever the current location is, these 2 lines of code will print the name and the exits, even if I add more rooms to the data structure. So you can see how a data structure and code can be designed together to make a general and extensible system, and that is desirable because it makes the code short, easy to understand, and it makes the system easy to extend without messing with the logic. Now, how do we shorten up our code that moves the player to the new location? What I want to do is take the direction the player gave us, which is now the letter N, S, E, or W, and use that letter to index into the list to get the index of the new location. So if they said N, then I want to turn that N into the index 3 and use that to find either -1 or the index of the room we're moving to. You'll notice that in directions, I have N, S, E, and W in order. So I'm going to get the index of the user's command in directions with index. Remember that command? I'll annotate a variable location index of type int. And after I shorten the command to a single character, I'll assign location index equals directions dot index command. We already know that command will hold N, S, E, or W, so we don't have to worry that the string won't be in that list. What that will return is 0 if command is N, 1 if command is S, 2 if command is E, and 3 if command is W. We need to add 3 to that to shift that index to 3, 4, 5, and 6 rather than 0, 1, 2, and 3. I'm going to add the constant north to that. I'm adding the constant north, the location of north in the sublist. That will shift to the appropriate index. I'll then check if the value at that index is an index into the list or a -1. I have to get added, so if Abby sub current location sub location index is not equal to -1, colon, then I'm going to set the current location to that index. Current location equals Abby sub current location sub location index. If you want to give them feedback on a bad move, you could add an else and print you bumped into a wall. Now let's print the new location and the new exits. So that's it. I can change the value of current location and run the program, and I'll always get a correct description of the current location and the exits, and I'll always be able to move appropriately from that location to a new location. Our data structure defines what the engine should do for different commands, so the engine only needs to index properly into the data structure to function. Growing the data structure, as long as we follow the structure we set down, will make no difference to the engine. In the next video, we'll look at how to wrap this in a loop so the player can explore the whole dungeon until they choose to quit. For now, practice with this. This is a lot. Lists aren't difficult to understand, but navigating a complicated list can be very intimidating. Practice quizzing yourself on the indices into different parts of this list and confirm you're correct in the console. Add rooms to this dungeon to make sure you understand how to hook another room into the map. See if you can write the code to describe the room by tapping into the description part of the sublist for the current room. When you're feeling confident with nested lists and indexing, join me for the next installment of Adventures with Python. As always, have fun and keep coding.